Hey everyone, I'm Anuj and I'm going to be talking about improving password generation. So password managers help users generate random passwords, strong passwords, which help them secure against guessing attacks. But prior research has shown that users tend to underutilize the generation aspect of password managers. These prior works are our primary motivation, especially Ish et al., in which we do observational interviews with password manager users, and we see that usability issues with generated passwords can lead to users avoiding generating passwords using password managers altogether. One of those usability issues is that the websites have weird composition policies that reject all the generated passwords by password managers. So how do we improve the experience for the user? The solution we come up with is a PCP description language with two goals in mind. It should be able to describe the PCPs that we find online. Second would be it should be easy to read and write, so it's not a hassle of its own to manage. For our first goal, we gather geographically diverse PCPs online. We collect one from at least a country from every continent, every 6 continent, and then we add countries with high levels of internet censorship on it. All in all, we gathered websites from Alexa top sources and Quantcast. We end up with 626 unique websites from all the countries. After all the deduplication, removing websites that do not have accounts that rely solely on SSOs and which require different materials such as bank accounts and identification numbers or have the same backend such as Google and YouTube, we end up with 270 unique websites. So using those unique websites, we built a description language. We started with a simple JSON-based base language, and then we iteratively encode all of the 270 unique PCPs. If there's one of the PCPs that's difficult to encode, we add features to our language so that all of them are easy to encode. Once we're happy with the language that we built, we solicit some feedbacks from our colleagues to further strengthen it. So we end up with a PCP description language, which has these features. It supports custom character sets. It supports minimum, maximum, and consecutive character lengths for the whole passwords or different character sets. It supports required character sets and subsets such as one of digits or symbols. It supports required and prohibited locations such as a password cannot end with a symbol. And something that's novel to our PCP language as opposed to other ones that were out there is it supports multiple sets of rules. So let's look at some examples. This one's from facebook.com, which is 6 characters long, digits, alphabets, and symbols. This one's from BBC, which is 8 to 50 characters, alphabets, and then digits or symbols. This one's from GitHub, which is either a short, complex password or a 15-character or long, simple password. So with our PCP description language at hand, we'll look into some of the uses that it has. The first and the most obvious one is password checking. We develop libraries in Python and JavaScript and put it online on PyPy and NPM. Administrators can define a PCP once and can use our libraries on both server and client side to validate their passwords. Second, generating passwords, we implement a proof of concept on Bitwarden that fetches the PCP that has been deployed on the website and then generate passwords which is compliant to the PCP. And thirdly, we use the PCP itself to calculate the search space as its strength, and that can be used to check if a PCP is strong enough before deploying it. Something novel about our PCP strength checking algorithm is we have found out that humans aren't a password generator, so they do not create random passwords. Humans have preferences, Previous research has shown that Chinese users prefer numeric characters, US users prefer alphabetic characters. And these preferences impacts the strength of password built on a PCB separately. Our PCB strength algorithm takes that into account and calculates the actual strength using human preference in mind. We evaluate our language and tooling using a user study in which participants encode 5 PCBs of increasing difficulty. Our metrics of success are correctness, completion time, and perceived usability. The demographics were university students, 52% of them graduate students, 76% male, and 92% computer science students. We use students as an act-in for software engineers, as they'll be entering the workforce shortly, and they'll be the ones managing the authentication code in a year or so from now. So the results of our usability study is, apart from policy 5 and apart from 2 users who got almost everything wrong, the results are almost perfect there. The time required is 30 seconds to 4.5 minutes, so not so much for users, some of whom did not even know what a JSON was when they started. And even for policy 5, the errors were from JSON formatting errors, such as forgetting to close a bracket, or minor errors, such as forgetting to exclude a period or a comma from the PCB. So now, using our strength checking algorithm, we analyze our web PCBs. We take works from Florenzi and Meyer, published in SOUPS previously, and analyze our PCB data set using our algorithms. And we try to compare it with the previous efforts. The improvements of our methods on those methods are: we have a larger data set with 270 unique websites. We have a greater geographic diversity. The work's only focused on US and Germany. And we have a more precise strength estimate for PCBs, as it takes into account all the composition stuff and also the human preference as well. So let's look at some of the results here. Results are kind of surprising. If we look at Chinese users who prefer numeric characters, as have been seen in the previous research, we see that half of the passwords are not even secure against online attacks, which is dangerous, at least. Looking at US users, also, like almost all of the passwords are not secure against offline attacks. And even if you use a password manager and you generate completely random passwords that are just enough for the PCBs, half of them are not secure against offline attacks. We also see a correlation between strength and the popularity of the website. So the more popular a website is, more stronger the PCB tend to be. Comparing with NIST recommendations, we see that 40% have a minimum length of at least 8. Less than 30% have no maximum length restrictions. 65% have no character composition requirements, which is good. But if paired with a minimum length, a good enough minimum length, but that was not the case for the PCBs that we had. So PCBs that did not have composition requirement had a suboptimal minimum length requirement as well. So comparing with the prior analysis, we see that PCB have grown over time, but it's just not enough. The PCBs are still not, passwords generated on the PCBs are still not resilient against offline attacks. Most of the PCBs still exist in those offline-online chasm. There's a correlation between PCB and the PCB strength and the popularity of the website. And like past research, different features such as ads and public usernames do not have any correlation with the strength of the PCB. With that, I'd love to take questions.